All right, guys, welcome to our next installment. Today, we're going to start talking about protein folding and protein stability. Now, to this point, we've been talking about some really important aspects of protein structure. We've been considering things like basic elements of secondary structure, alpha helices and beta sheets, and how they're held together, the importance of the hydrogen bond in putting those or specifying those pieces of protein secondary structure. We've talked a little bit about some of the other weak interactions that are important for biomolecular structure. And today, we're going to begin the process of putting those ideas together and thinking about how and why proteins are stable and how they fold into the three-dimensional structures that give them function, right? Now, but to this point, we've pretty much, when I've talked about protein structures, I've shown you various motifs and examples of protein structures. We sort of just took for granted that proteins just sort of look that way, right? The way they look in the PDB, right? Of course, that's not what happens. Proteins don't just spring into existence looking like that. They're synthesized as linear chains of amino acids, as we all know. And they have to acquire that structure post-translationally, or in some cases co-translationally. And they have to do it with high fidelity, right? They have to do it essentially every time. They need to do it reliably. And amazingly, all the information necessary for that process to take place is encoded in two places: that linear sequence of amino acids, that specific identity of amino acids at particular positions down that polypeptide chain, and the environment in which that polypeptide chain is found, right? And the expectation for that linear sequence of amino acids that is sort of encoded by evolution is that that polypeptide is going to be in an aqueous solution at a given temperature and pressure, and therefore will form that particular structure. Now, that idea that all that information is encoded in that linear specific sequence of amino acids and then the surrounding environment is an amazing idea, right? And that idea was first suggested by the work of a famous protein chemist of a previous era by the name of Christian Anfinsen. And this idea, when it was first proposed, this idea that all that information needed to fold a polypeptide was encoded essentially in the thermodynamics of that polypeptide in an aqueous and appropriate aqueous environment, was kind of shocking, almost heretical at the time. There were ideas of vitalism in biology, and this makes biology seem so chemical, so based in physics, and there was some resistance to this. But Anfinsen was right, at least to a first approximation. And he won the Nobel Prize for this in the 1970s. Right? So let's think a little bit as a way to set the stage of the protein that Christian Anfinsen worked on, right, where he did much of his work. It's a small RNA degrading enzyme by the name of RNase. You've probably heard of it. Specifically, the variant he worked on was RNase A, right? It's, like I said, a relatively small protein. It's about 124 amino acids, right? Very stable protein, super important for many organisms' defense against RNA genome viruses. Bane of the existence of anybody who's ever worked in an RNA lab or tried to produce RNA, because we secrete it like crazy in our tears and our spit and our saliva. It's everywhere. It turns out to be a really good model for looking at and understanding some important things about protein folding, right? So we're going to think about protein folding, right? We're going to do the same sort of extrapolation to simple model to figure out what we can test predictions of and what that model allows us to say in the most quantitative way possible. So let's write down an equilibrium for the folding of RNAs, right? So if we're going to do that, we might use a nomenclature that looks something like this. So let's say the unfolded state of RNase, I'm going to represent that with a U, right? So this would be, like I said, the unfolded, right? Or in another nomenclature you'll probably hear me use, others use, is the denatured state. And then let's presume, right, as it's true, that that unfolded state is in equilibrium with the folded state, which we're going to represent with an N. And that also means the native state or the folded state, right? Okay, so here's some questions. Assuming that's our configuration, the first question that would fall out of this that we want to try and understand is why? Why is it that protein, these folded protein structures, are stable? Why is that, right? And then the second question, once we sort of get a handle on that, the second question we need to deal with is how, right? Does a protein find that three-dimensional structure? Let's put it a better way. Find a unique 3D structure, right? Okay, so today, for the lecture, let's deal with this first problem. Let's see if we can come up with a set of principles based in the thermodynamics of that polypeptide chain, thinking about it in very much the way that Amphitson and people who followed him thought about it, to understand why it is that a polypeptide is stable, or a folded protein is stable. Okay, so to do that, let's rewrite that equilibrium a little bit in a way that sort of reflects what we know is true, which is that we have that unfolded state. We write the equilibrium native. We know it probably looks something like that, right? Because the idea is that we know this protein is stable, so that equilibrium is going to fall much more towards the native state protein. And let's assume also that we're at, physiologic temperature, pressure, solution conditions, etc. Right? Okay, and we know that's going to have an associated equilibrium constant. We're going to use K like we've been doing. And we know we can define that equilibrium constant as K equals the concentration of the native state divided by the concentration of the unfolded state, right? Okay. And we know, based upon some discussions we've had in class, that if I know the equilibrium constant, I know how to calculate the free energy, right? You guys remember that. Once I can measure, if I can measure K, I get this basically for free. I know the free energy, right, at equilibrium has to just be minus RT, natural log of that equilibrium constant, right? Which is cool, because I also know that because the protein is stable, because if I took that protein unfolded, it would spontaneously form in the native folded state. This also has to be less than 0, right? The delta G for that reaction, that's sort of an expression of that equilibrium, has to be less than 0. Therefore, the folded state of the protein is stable. Okay. Things we've talked about before, we know that therefore means there must be a driving force. There has to be a chemical potential that pushes that unfolded protein, that unfolded polypeptide, into its native conformation. So where's it come from? Okay, kind of like we've done at least once before, we can break that free energy down and get a look at the constituent underlying components of the Gibbs free energy and get some really interesting mechanistic insight. So when we do that, for RNAs at 25 degrees C, you see the following, right? It's that the standard state enthalpy change, and again, I'm going to write this so you just remember, right? Talking about, left to right, unfolded to the native state, right? the free energy change, the enthalpy change is minus 280 kilojoules per mole, right? So that's cool. That's great. That makes some sense, right? And just to help you remember to keep the Gibbs equation in mind, delta G equals delta H minus T delta S, right? Okay. So that makes sense, right? We know the protein's stable. We know that for this reaction, for the protein to be stable, that has to be less than 0. Okay. Delta H here is minus 280 kilojoules per mole. So that's going in the right direction. The enthalpy change for folding the protein is stabilizing. It's going to help drive that reaction. It's an exothermic process. Okay, so cool. That's great. All right. Delta S for going in the folding direction, however, is minus 0.8 kilojoules per mole. Which means, of course, that T delta S is now going to, or excuse me, I should say, minus T delta S, remember from the Gibbs equation, second half, the work function, is equal to plus 235 kilojoules per mole. So you look at that and you're like, whoa, wait a minute, right? Like, oh, big red flag here, right? Oh my goodness. The entropy change, the folding of the polypeptide, is negative, which means minus T delta S is largely positive, which means in the sum of the Gibbs work function, the entropy change is opposing folding, and by a lot, right? That's a big oppositional contribution to the spontaneity condition we need, which is the Gibbs free energy being less than 0. Man, okay, well, all right, so that's not awesome, but you know, it's okay, because if we sum this whole thing up, right, we take this whole thing, we put together, we know then delta G for folding of the protein, right, is still gonna work because we got minus 45 kilojoules per mole of free energy to work with. So again, whew, right, that's great. The protein folds, it's stable, but notice something. That's only sort of just stable. Just, right? Just for reference, right? Do you know what the free energy, you guys remember, you may or may not remember what the free energy of ATP hydrolysis is under sort of normal cellular conditions? If you don't remember, I'm going to remind you here before too much longer. Turns out it's sort of in the range of 45 kilojoules per mole, right? It's in the range of 40 under cellular conditions to 50 kilojoules per mole for ATP hydrolysis, which means this protein, when this is a really stable protein, by the way, RNase A is that's one of the reasons it's, you know, such a good model for doing this. RNase A is sort of only stable to about the free energy available in a single ATP phosphodiester bond, right? And there's a huge, if you look at this, in addition to the fact that it's only just stable, there is an enormous entropic barrier opposing that folding. I mean, it still happens, right? But there's a big entropic barrier in the way. So what's going on? All right, well, think about it this way. So let's think about RNase A again, and we're gonna write down a toy model to try and illustrate this idea a little bit, right? So let's again consider RNase A Like I said, it's a 124 amino acid protein. But let's just just for the sake of this simple model, let's just round that off. Let's just say, yeah, it's about 100 amino acids, right? For the purposes of this calculation, makes it easier. All right, 2, let's assume that in this toy model of RNA-seq, we're only going to allow, you've got to be kidding me. Let's assume that only 3 configurations are allowed for each phi psi bond, right? You remember the phi psi bonds looking from the alpha carbon. So we're only going to allow 3 configurations per phi psi bond. So each amino acid, right, would have 3 possible configurations around those 2 bonds. Now that's a stupid oversimplification. There's certainly more than that. But, the numbers this big, getting it more accurate doesn't change the first order conclusion we're going to draw. So again, this makes the calculation simpler. So if we sort of think about a toy model like that, 100 amino acids, 3 configurations per phi psi bond, that would mean then that we have possible configurations, 3 to the 2 times 100 possible conformational states. Available to this protein, right? In principle, right? Okay, so using the statistical mechanical definition I gave you guys of entropy, right? Remember that S equals K natural log of W, right? Well, what we can do is we can set W equal to that 3 to the 2 times 100 possible conformational states. We're going to assume that that is equivalent, those possible conformational states, or that space is equivalent to the system degeneracy, which means we can then define a configurational entropy for this toy protein as being equal to K log of 3 to the 2 times 100. Now, this is, again, is an oversimplification, right? This would only even, in this toy model sense, be true, assuming that all of these states are isoenergetic, right? Which is undoubtedly, certainly would not be the case. But again, for numbers this big, even if we're off a bit here, it really doesn't change the conclusion we're going to draw. Okay, so with that set of assumptions, we can now calculate then the configurational entropy available to this polypeptide, right? In the unfolded state, right? Assuming this thing is unfolded, right? And we got 3 possible configurations around all phi psi angles, we can specify more or less the configurational entropy available to that unfolded polypeptide. And what it would have to be, and I'm just going to put a little U there for unfolded, the configurational entropy of the unfolded state, based upon that set of assumptions, would be about 1.8 times 10 to the 3 joules per Kelvin, right, per mole, right? Okay, what about the native state? So if you think about the native state, this is for the unfolded state of the protein in our toy model. How about the native state? Well, we can make a fairly simple approximation here. Let's assume that the native state, right? Let's assume the native state is represented by only one configuration. There's really only one state of this protein when it folds. Again, that's probably not completely true. There's certainly more flexibility on that, for any real protein. It's not going to be a single completely unique state, but again, it's not a bad approximation in our toy model of what's going on here. Okay, so if that's the case, we can now calculate the configurational entropy for the native state, which is simply going to be equal k natural log of 1. We know what the natural log of 1 is, right? That's going to be 0. Which means the configurational entropy of the native state is essentially 0. So the difference we have between the native state and the unfolded state is something like 2 kilojoules per mole in loss of configurational entropy, right? You have to, all that configurational entropy in the unfolded state, even in the story, and you've got to crush that all the way down to a single state. That's a big loss of entropy. And that's the reason for that large entropic barrier to folding that we see when we actually do an experimental measurement. The data that what I've written down here, this is actual experimental data. This is what the real numbers work out to be when you do this with RNAs, right? So that entropic barrier is real, and this simple toy calculation sort of explains, or hopefully helps you understand that difference, right? Okay, because we have the unfolded polypeptide has to shed a lot of configurational entropy to get down to a much smaller number of tightly arranged states. Okay, and this happens, of course, because, as I said, delta S, right, is less than 0, which means that T delta S, right, or minus T delta S, is much greater than 0. It's large and positive, and that has this inhibitory impact on the Gibbs free energy change for folding of the polypeptide. Okay, so that, right, is sort of this entropic barrier to folding, which is all wrapped up in the loss of configurational entropy of the polypeptide chain. All right, fine, but it still happens, right? Somehow it still happens. This is an example of a question I posed to you guys earlier when we talked about the second law. Can entropy ever go down? And I answered that question with a sure, can. If you think about the freezing of water into an ice cube, that's a loss of entropy of the water as it forms an ice crystal. Here's another example. Folding of a polypeptide represents a local loss of entropy. The polypeptide sheds must lose configurational entropy in order to fold. But just like with the ice, you got to pay the price. Somehow, there's a way to compensate, and to compensate just enough to get that protein stable by about 45 kilojoules per mole. All right, so the question then is, how does that happen, right? And that cost, the cost of that entropic barrier, the cost is paid in 2 ways, right? The first has to do with the hydrophobic effect. And the second has to do with all those weak interactions. And how that works and why that works, we need to think about in a little more detail. We'll come back to that next.